Back in 2016, Elon Musk unveiled his plan for colonizing Mars. According to that plan, the first crews were supposed to head for the Red Planet as early as 2024. On paper, it all looked perfect, but now it's actually 2024 and there's still no real progress. Why? Problem number one: gravity Mars is about half the size of Earth. Its equatorial radius is 3,400 kilometers, just 53.2% of Earth's. The mass of the red planet is even smaller in comparison, around 6.4 times 10 to the 23rd kilograms, which is only 11% of Earth's mass. According to Newton's classical theory of gravitation, that means everything on Mars experiences a much weaker gravitational pull. The surface gravity on Mars is just 3.7 meters per second squared, about 2.6 times less than on Earth. That doesn't sound so bad at first. In fact, with lower gravity, rockets need less velocity to escape Mars and return home. That means engines can run at lower power, consume less fuel, and so on. And what's the downside for humans? So you jump higher when you walk. Big deal, right? Not quite. Research shows that long-term exposure to low gravity, like what you'd experience on Mars, can lead to loss of bone mass from 1 to 1.5%. Our skeleton becomes less dense and more fragile, increasing the risk of injury. Atrophy of postural muscles, the so-called anti-gravity muscles. These are what keep our bodies upright. With less gravitational force, they weaken from disuse. Fluid redistribution in the body. The classic issues include puffiness in the face and a loss of taste and smell. Cardiovascular problems. The heart doesn't have to pump as hard as it's designed to under Earth's gravity. Of course, these effects on Mars aren't as extreme as in microgravity, like aboard the ISS. And it's true that record-holding astronauts like Russia's Gennady Padalka didn't become disabled after 878 days in orbit. Still, even he needed a long period of recovery. And colonists on Mars won't be staying for 2 or 3 years. They'll be living there for decades. Sure, the adult body will adapt eventually, but what about long-term health? What about the impact on children born and raised in Martian gravity? That's a huge unknown. More research is needed. How to fix it? One proposed solution is using centrifuges to simulate gravity and keep the body in shape. Imagine a giant ring-shaped train, constantly spinning, where people live and sleep. Of course, it'll need a powerful energy source to keep it moving. Problem number 2. Radiation Earth is protected by the Van Allen radiation belts, which shield us from dangerous cosmic radiation, including galactic cosmic rays or GCRs, which are born from exploding stars. This protection exists thanks to Earth's magnetic field. But Mars doesn't have a magnetic field, and that means no radiation belts. It's the same with Venus and Mercury, and they're fully exposed. As a result, cosmic radiation hits the Martian surface without any barrier. And Mars's distance from the Sun doesn't help much either. Since 2001, NASA's Mars Odyssey spacecraft has been studying the planet using an instrument called the Martian Radiation Experiment, or MARIE. Its data showed that the average radiation level on the surface is about 0.7 millisieverts per day, ranging from 0.35 to 1.15 millisieverts. Later, rovers like Curiosity confirmed those numbers. For comparison, the natural background radiation on Earth is just 2.4 millisieverts per year. That means a person standing on the surface of Mars would absorb a full Earth year's worth of radiation in just 2 to 3 days. That's 2 or 3 times more than astronauts get on the ISS. And remember, ISS crews aren't living there for decades. like future Martian colonists might. Now add the radiation exposure during the trip to Mars, about zero point 0.7 sieverts over 350 days, and the total dose becomes even more frightening. The consequences are well known. Radiation sickness, a significantly increased risk of cancer, and long-term health damage. How to fix it? First, we'll need to develop spacecraft with effective yet lightweight radiation shielding to protect astronauts from GCRs. Composite materials and advanced polymers are being actively researched for this purpose. They could help reduce radiation exposure during flight. Second, long-term survival on the Martian surface will require underground shelters with extremely thick walls, something like high-tech bunkers. But that means sending massive construction equipment across millions of kilometers and making sure it has fuel to operate. We'll talk more about that later. There's also a sci-fi option, creating artificial magnetic poles and generating a Van Allen belt around the entire planet. Research is being done in this direction too, but don't expect it to become reality anytime soon. Problem number 3. Temperature life on Earth is possible largely thanks to a perfect balance. The right distance from the sun, the tilt of the planet's axis, the rotation period, and so on. All these factors combine to create a stable, livable climate. With Mars, it's a different story. The planet is much farther from the sun. Its year is 687 Earth days long. At most, the Martian surface receives about 590 watts per square meter of solar energy, much less than Earth. Because of this, the average daily temperature on Mars is minus 53 degrees Celsius. At night, it can plunge to minus 128 degrees Celsius. And even at noon, when the sun is at its highest, the temperature might barely reach plus 27 degrees Celsius. And only for a short time. Obviously, these extreme and rapid temperature swings are completely unsuitable for human life. Data from NASA's Curiosity rover, including graphs of air and ground temperatures, confirms just how harsh and unstable the Martian climate really is. How to fix it? The simplest option is to build heated living modules on the surface. But where will all that energy come from to keep such large spaces warm? Another idea: go underground. Below a certain depth, temperature fluctuations become much less severe, and you might even tap into heat from Mars's core. But we don't yet know the exact thermal gradient, so we can only guess how deep we'd have to dig. Still, we're not talking about a few meters. It might be several, or even dozens, often of kilometers. Building an underground city at that depth would be a monumental engineering challenge. There are also wild theories involving planetary-scale terraforming, like heating the Martian atmosphere using enormous orbiting mirrors 125 kilometers across to focus sunlight. With all that carbon dioxide in the atmosphere, the resulting greenhouse effect could gradually raise the planet's temperature to livable levels. Problem number 4. Atmosphere. Earth's atmosphere is perfectly suited for life. It's made up of 78% nitrogen, 21% oxygen, and about 1% other gases. Carbon dioxide is just 0.03%. Even a small change in that balance can have noticeable effects, like the climate issues we face today. Atmospheric pressure at sea level is around 1,013 millibars. Even slight deviations from that, like at high altitudes or underwater, are immediately felt by the human body. On Mars, the atmosphere is much thinner, and its composition is anything but friendly. It's made up of 95% carbon dioxide, 2.7% nitrogen, 1.6% argon, and only 0.14% oxygen. Pressure is just 6 to 7 millibars. That's 0.5% of Earth's, well below what's known as the Armstrong limit. Without a pressurized suit and an oxygen supply, humans wouldn't last more than a few seconds. How to fix it? First, we'll need to bring a large reserve of breathable air, enough to last for years, along with systems that maintain livable pressure in habitats and spacesuits. But air runs out eventually, so it will have to be replenished somehow, either transported from Earth or produced on Mars. One promising approach is being tested with the MOXIE experiment on the Perseverance rover. MOXIE uses solid oxide electrolysis to extract oxygen directly from Mars's carbon dioxide-rich atmosphere. If successful, this could reduce our dependence on resupply missions from Earth. As for terraforming, things get way more complicated. Mars's polar ice caps contain large amounts of frozen CO2 and water. Elon Musk once proposed detonating nuclear bombs over these caps to release the gases, increase atmospheric pressure, and warm the planet through an enhanced greenhouse effect. But that wouldn't solve the bigger issue: the air's composition. We'd just end up with more CO2, not oxygen. And recent studies show that even if we released all available reserves on Mars, pressure would only increase to about 7% of Earth's. Still far too low. Honestly, it seems Musk may have been joking. Problem number 5. Dust storms Mars isn't actually red, at least not if you look at it from orbit. But through a telescope, it appears reddish because its thin atmosphere is filled with dust particles and Martian regolith mixed with iron oxide. Due to thermal gradients and uneven heating of the surface, Mars experiences strong winds that stir up this dust and keep it suspended in the air. Sometimes these become full-on dust storms, but because the atmosphere is so thin, and there's virtually no water vapor to bind the particles together, these storms aren't destructive in the way they're shown in movies. That iconic dust storm scene from The Martian, yeah, not very realistic. The real issue is different. These storms block sunlight and cover solar panels with dust. That's why during one of the largest dust storms, NASA had to put the Opportunity rover into low power mode and wait for things to clear up, just to conserve enough energy. How to fix it? Let's set aside the more far-fetched terraforming ideas like bind the dust with water vapor. The simplest answer is don't rely on solar power, especially since, as mentioned earlier, Mars gets far less sunlight than Earth. The better approach is to have alternative energy sources and powerful backup batteries, enough to keep a Martian colony alive through weeks of darkness. Problem number 6. Water is something we take for granted on Earth. Our planet is 70% covered in it. Oceans, seas, rivers, lakes. But Mars is different. Even though it's half the size of Earth, its land area is about the same. But there are no open bodies of water. Still, surprisingly, Mars has a decent amount of water, about 5 million cubic kilometers. For comparison, the Black Sea holds around 550,000 cubic kilometers. Most of Mars's water is locked in the polar ice caps, frozen solid. If we could melt all that ice, it would provide enough water for a large colony for many decades. The challenge is that because of the low temperatures and extremely low atmospheric pressure, liquid water can't exist on the Martian surface. It sublimates, turning directly from solid to gas. How to fix it? NASA scientists are working on ways to convert ice directly into vapor using microwave radiation. The idea is to collect that vapor and then condense it into liquid form under controlled conditions, like inside a habitat with Earth-like pressure. In the long run, this wouldn't just solve the water problem, it could help with food too. Hydroponics is very much on the table, and experiments show that Martian soil, or regolith, has a decent pH and enough minerals to support plant growth. Water could also be split into hydrogen and oxygen through electrolysis, providing breathable air and fuel for the colony. Problem number 7. Meteorites. Earth is well protected from small space debris and meteorites by its thick atmosphere. Most objects burn up before they ever reach the ground. Sure, exceptions like the Chelyabinsk meteor exist, but in general, impacts here are rare. Not so on Mars. Its atmosphere is far too thin to offer real protection. As a result, the red planet is constantly bombarded. Every year, up to 200 meteorites strike its surface, enough to pepper the landscape with thousands of visible craters. So, what are the chances of a meteorite hitting a human colony? Probably lower than the risk from radiation, but still real enough to take seriously. How to fix it? If the main parts of a Martian colony are built underground, for radiation protection and thermal insulation, then meteorites won't pose much of a threat. Of course, you could imagine a scenario like Armageddon, with a battle-ready spacecraft and Bruce Willis in a spacesuit with a giant drill. Or maybe orbital satellites armed with lasers to deflect incoming asteroids. But honestly, meteorites aren't the biggest problem when it comes to colonizing Mars. Problem number 8. Construction Mars is a brutally hostile environment. Cosmic radiation, extreme cold, unbreathable air, and more. To survive there, we'll need a lot of infrastructure. Everything from technical systems for extracting water and generating power, to massive living complexes with thick radiation-shielding walls. And if we end up building an underground city several kilometers deep, that raises even more questions. How do we dig that deep? What tools and materials do we use? Where do we get them? For comparison, the Curiosity rover cost $2.5 billion and weighed only 900 kilograms. Now imagine trying to deliver a giant excavator or hundreds of tons of building materials over 55 million kilometers. It's a logistical nightmare. Right now, the most powerful rocket system we have is SpaceX's Starship. In theory, it could deliver up to 150 tons of cargo to Mars, but building a whole colony will require many, many trips. How to fix it? One option is a modular construction system, like the International Space Station. One flight delivers a water extraction module. Another flight brings a living quarters with radiation shielding. Ideally, everything should be assembled autonomously, so that when the crew arrives, the base is already ready, and they're not stuck trying to bolt it all together in the middle of a dust storm. Another idea is to minimize what we bring from Earth by using Martian resources for construction. Scientists at the University of Manchester have developed a new kind of concrete made from local regolith and a binding agent. Basically, potato starch from crops grown on Mars. The result has a decent compressive strength of up to 25 megapascals. It's still experimental, but the concept of don't bring everything with you has a lot of potential. Problem number 9. Energy without stable and reliable energy sources, there's no surviving on Mars. Electricity is vital for everything, even splitting water into oxygen and hydrogen through electrolysis. If your power goes out during a dust storm that lasts for weeks, colonists could quickly run out of water, heat, or air. How to fix it? There are a few potential solutions. Solar power. It's a decent backup option, but not something you can fully rely on. Dust storms can block sunlight for months, and overall solar intensity on Mars is much lower than on Earth. Wind energy. Sounds promising at first. Martian wind speeds can reach up to 100 kilometers per hour. But due to the thin atmosphere, wind turbines generate very little actual power. Still, some researchers are exploring ways to make it work. Nuclear power. Now we're talking. RTGs, radioisotope thermoelectric generators, are already used on missions like Curiosity. But NASA has gone further and developed a new system, Kilo Power. It uses a Stirling engine and uranium-235 fuel. The heat from nuclear fission is transferred through pipes filled with liquid sodium. Output: up to 10 kilowatts of steady power with a 10-year lifespan. Hydrogen and methane. If we can extract water on Mars and split it via electrolysis, the resulting hydrogen can be used to create methane using the Sabatier process. Just like on the ISS. All you need is hydrogen and CO2, which Mars has in abundance. The methane could then be used both as fuel and as a power source for the colony. Geothermal energy, technically possible but much less effective on Mars than on Earth. The core is colder and there's a lack of active underground heat sources. Problem number 10, psychology. After all the technical issues we've covered, it might seem like psychology should be the least of our worries. Who has time to think about loneliness or homesickness when there's no oxygen or water? But in reality, psychological challenges are very real. They're well documented, including in scientific journals like Clinical Neuropsychiatry. Some of the most common issues include feelings of isolation, spending years in a confined space with a small group of people, no privacy, no new faces. Psychological compatibility becomes critically important. Constant anxiety. The fear that something might go wrong, a system failure, a medical emergency, a sudden silence from Earth. And the worst part? You're powerless to fix most of it. Lack of solitude. Many people need time alone to recharge. In space or on Mars, that's a luxury you won't have. Disrupted sleep cycles, excess light in the modules, constant background noise from equipment, low gravity. All of this messes with circadian rhythms and sleep quality. On the ISS, these problems already exist, and astronauts are only there for a few months. They know they'll return to Earth. But Martian colonists, they may never come back. They'll never swim in the ocean again, or lie in the grass or hear wind in the trees. That thought alone could be deeply depressing. On top of that, communication with Earth has a 20-minute delay. So, there's no such thing as a real-time conversation, and no quick help if something goes wrong. How to fix it? NASA plans to invest heavily in psychological preparation. That includes simulating the Martian base environment down to the smallest detail, and keeping potential colonists inside for long stretches to monitor how they react to stress, conflict, and isolation. Because the stakes are huge. One argument, one breakdown, one person losing control, and the entire mission could be in jeopardy. Why do we even need Mars? Why is humanity so determined to reach it, to build a base there, and eventually a colony? This isn't just Elon Musk's ambitious dream. It's a strategic move for survival, progress, and the future of our species. First, Mars is our plan B. Right now, all of human civilization exists on a single fragile planet with a vulnerable ecosystem and limited resources. We're exposed to existential threats: nuclear war, asteroid impacts, supervolcanoes, pandemics, even self-inflicted disasters. Colonizing another world gives us a lifeline, a second chance if something catastrophic happens on Earth. Second, settling Mars would trigger a wave of scientific and technological breakthroughs. Living on another planet forces us to solve problems we've never faced before. Sustainable energy, closed-loop life support, radiation shielding, autonomous manufacturing. These innovations would benefit not just space explorers, but life on Earth. from remote communities to disaster zones and beyond. Third, it's the next step in our evolution. Humans are explorers by nature. We crossed continents, sailed oceans, reached the skies. Now it's time to step onto other worlds. This isn't just about geography, it's about becoming a multi-planetary species, and maybe one day, even interstellar.